Imagine a universe where the fundamental constants, the speed of light, the strength of gravity, the mass of an electron, weren't etched in stone, but chosen by a cosmic dice roll at the dawn of time. For decades, we've treated these numbers as immutable, the bedrock of reality. Yet, their values appear unnervingly just right for stars to ignite, for atoms to form, for life itself to emerge. What if this precision isn't divine design, but a statistical fluke within an infinite expanse of possibilities? The tension is palpable. Are these values truly universal, or are they mere frozen accidents specific to our pocket of the cosmos? The standard model of physics provides no explanation for the precise values of constants, like the fine structure constant or the proton-electron mass ratio. It simply accepts them as given. But theories like string theory's landscape suggest a vast multiverse, an almost infinite number of universes, each with its own unique set of physical laws and constants. We, by necessity, find ourselves in one of the vanishingly few where chemistry and complex structures can arise. This isn't just philosophical musing. It redefines our very understanding of existence. If our fundamental laws are merely a localized outcome, what does that imply about their stability? Consider the fundamental forces that sculpt our reality. The strong nuclear force binding quarks into protons and neutrons, the weak nuclear force governing radioactive decay and stellar fusion, electromagnetism holding atoms together and orchestrating chemistry, and gravity shaping galaxies and dictating cosmic evolution. Each is quantified by a coupling constant, a dimensionless number that dictates its strength. If the strong nuclear force were just a few percent weaker, atomic nuclei couldn't form, leaving a universe devoid of stable elements beyond hydrogen. If it were slightly stronger, hydrogen would fuse too readily, collapsing into helium and heavier elements without the long-lived stable stars necessary for complex chemistry. The delicate balance is breathtaking. Then there's the fine structure constant, alpha, approximately 1/137. This seemingly innocuous number governs the strength of electromagnetic interaction, influencing how electrons orbit nuclei, how light interacts with matter, and ultimately the size and stability of atoms. If alpha were significantly larger, electrons would spiral into nuclei, making stable atoms impossible. If it were smaller, chemical reactions would be too slow and light interaction too weak to support complex structures. It's a cosmic dial, exquisitely tuned. Even the masses of fundamental particles are critical. The electron's mass, for instance, in relation to the protons, is crucial for determining the size of atoms and the nature of chemical bonds. Alter these ratios even slightly, and the universe we inhabit, a universe capable of forming planets, water, and carbon-based life, simply wouldn't exist. This uncanny precision, this profound fine-tuning, has haunted physicists and cosmologists for decades. It's like finding yourself in a casino where, against astronomical odds, every single roll of the dice has landed exactly on the numbers required for you to win the cosmic jackpot. Is it luck, or is the casino rigged? This leads us to the anthropic principle, a concept that attempts to address this fine-tuning. In its weak form, it simply states that we observe the universe to be as it is because, if it were significantly different, we wouldn't be here to observe it. It's a selection effect, not an explanation for the constants' values themselves. But the strong anthropic principle goes further, suggesting that the universe have properties that allow for the development of intelligent life. This borders on teleology, a concept many scientists are uncomfortable with, as it suggests a purpose or design rather than a natural mechanistic process. The truly mind-bending alternative comes from the theoretical realm of the multiverse. What if our universe isn't the only one? What if it's just one bubble in an infinite, frothing cosmic ocean, a multiverse where every conceivable combination of fundamental constants and physical laws is realized in different universes? In this scenario, the apparent fine-tuning of universe isn't special. It's just that we, as observers, necessarily inhabit one of the universes where the constants happen to be conducive to our existence. The vast majority of other universes would be barren, ephemeral, or simply incapable of supporting any form of complexity. This idea is deeply embedded in some of the most advanced theories attempting to unify physics, particularly string theory's landscape. String theory, in its quest to reconcile quantum mechanics with general relativity, predicts not a single unique vacuum state for the universe, but an almost unfathomable number, perhaps 10 to the 500 different vacua, each corresponding to a different set of fundamental constants, particle masses, and even the number of spatial dimensions. Our universe, with its specific values for the speed of light, Planck's constant, and the gravitational constant, would simply be one of these possibilities, a specific valley in this vast cosmic landscape. The implications are profound. If our universe is just one outcome of a cosmic lottery, then the laws of physics we painstakingly uncover might not be universal truths, but rather local rules. They are the frozen accidents of our specific corner of the cosmos, the particular settings chosen by our initial cosmic dice roll. This shifts the focus from finding a grand overarching theory that the constants to understanding the probability distribution of these constants across the multiverse. It forces us to confront the unsettling possibility that some of the most fundamental aspects of our reality are not derived from first principles, but are contingent, accidental properties. This isn't a dismissal of scientific inquiry, rather it's an expansion of it. It compels us to ask, can we ever truly test the multiverse hypothesis? What would constitute evidence for other universes with different laws? And if our laws are merely a localized outcome, what does that imply about their stability? Could these frozen accidents thaw or even change over cosmic time? The very fabric of reality, once thought to be eternally fixed, suddenly shimmers with an unsettling mutability. Following that unsettling thought, consider this. If our cosmic constants are frozen accidents, what if they aren't quite frozen? What if the universe is still in a state of subtle, perhaps imperceptible flux? The idea that physics laws could change isn't science fiction. It's a profound implication of certain cosmological models. We observe the accelerating expansion of the universe, driven by dark energy, whose nature remains one of science's greatest enigmas. Some theories propose dark energy isn't constant, but a dynamic quintessence field, a cosmic fluid whose energy density could subtly shift over eons, potentially altering the very fabric of spacetime and the constants embedded within it. Imagine a universe undergoing a cosmic phase transition, akin to water boiling or freezing, but on a grand universal scale. Such an event, possibly triggered by the decay of a hypothetical scalar field, could dramatically alter the fundamental forces, particle masses, or even the number of spatial dimensions. While current observations place stringent limits on constant variation over cosmic time, the possibility remains a haunting whisper in the data. If such a shift were to occur, the very stability of atoms, the light from stars, the mechanics of gravity, everything we understand could unravel, paving the way for an entirely new, unrecognizable reality. The question isn't just our laws or accidents, but the universe might roll the dice again. The notion of immutable physical constants has been a cornerstone of modern science since Newton. We've built our understanding of the cosmos, from the smallest subatomic particles to the grandest galactic structures, on the assumption that C, G, and H are fixed, universal values. Yet, a growing body of theoretical work, spurred by the fine-tuning problem and the mysteries of dark energy, suggests this might be too simplistic. What if these constants are not constants at all, but rather slowly evolving parameters influenced by the very dynamics of the cosmos they describe? One of the most compelling avenues for exploring this mutability lies in the enigmatic force we call dark energy. Discovered through observations of distant supernovae, dark energy is the mysterious agent responsible for the accelerating expansion of our universe. The simplest model, Einstein's cosmological constant, posits a fixed energy density inherent to spacetime itself. But alternative theories, like quintessence, propose a dynamic scalar field permeating the cosmos. This quintessence field would have an evolving energy density, and its coupling to other fundamental fields could, in principle, cause variations in the effective values of our fundamental constants over cosmic time. Imagine space-time itself not as a static stage, but as a living, breathing entity, its properties subtly shifting with the cosmic winds. The implications of such a dynamic field are staggering. If the fine structure constant were to change, for example, the stability of atoms would be compromised. Electrons might no longer be able to maintain stable orbits, leading to the disintegration of matter as we know it. The very bonds that hold molecules together, the chemical reactions that power life, would be fundamentally altered. Stars, whose luminosity and lifespan are exquisitely sensitive to these constants, would either burn out prematurely or fail to ignite altogether. The universe would become an alien landscape, its chemistry unrecognizable, its stellar nursery silent. Scientists are not idly speculating here. They are actively searching for evidence of such changes. One of the most famous natural experiments is the Oklo natural nuclear reactor in Gabon. Billions of years ago, a unique geological formation of uranium ore and groundwater created conditions for a sustained nuclear chain reaction. By studying the isotopic ratios of fission products from Oklo, scientists can infer the value of fundamental constants, particularly the fine structure constant, as it existed 2 billion years ago. Current analyses place extremely tight constraints on any variation, showing that alpha has changed by no more than a few parts per million over that immense timescale. Further evidence comes from observations of distant quasars. By analyzing the absorption spectra of light from these ancient, extremely luminous objects, physicists can probe the properties of matter in the early universe, billions of light years away. While some initial intriguing anomalies were reported, more precise and extensive data from telescopes like the Very Large Telescope and the Keck Observatory have largely constrained these variations to be negligible. The universe, it seems, has been remarkably stable for billions of years. But what if the change is not gradual but catastrophic? Enter the concept of a cosmic phase transition. Just as water can suddenly freeze into ice or boil into steam, the universe itself could undergo a dramatic shift in its fundamental state. This idea is rooted in quantum field theory, where the vacuum of space isn't empty, but a bubbling quantum foam, possessing a specific energy state. If the current vacuum is not the lowest possible energy state, a false vacuum, it could, theoretically, decay into a true vacuum. This vacuum decay would propagate through the cosmos as a bubble of new reality, expanding at nearly the speed of light. Inside this bubble, the very laws of physics would be rewritten. Fundamental constants could take on entirely new values. Particle masses could shift. The strong force might weaken, the weak force might strengthen. Even the number of spatial dimensions might change, collapsing some or unfurling others. Such an event would be an existential catastrophe, not merely altering conditions, but fundamentally redefining reality itself. Anything within the expanding bubble, stars, planets, life, would instantly cease to exist in its current form, transformed into something utterly alien, governed by a new, harsh physics. The universe would have, in essence, rolled the dice again, with potentially devastating consequences for any existing complexity. While such a phase transition is speculative, it's a legitimate area of theoretical physics, explored by researchers pondering the ultimate stability of our universe. The existence of the Higgs field, for example, and its specific mass, places our vacuum state in a precarious position, suggesting it be metastable. This means our universe could, given enough energy or a quantum fluctuation, tunnel into a lower energy state. The universe we inhabit, with its seemingly robust constants, might be living on borrowed time, unknowingly perched on the precipice of a cosmic cliff. The pursuit of these questions, are constants truly constant? Could they change? What are the implications? Drives physicists to push the boundaries of observation and theory. It forces us to reconsider the most fundamental assumptions about our reality. If our laws are mutable, then the future of the cosmos is far more unpredictable and wondrous than we ever imagined, and our understanding of it an ongoing, thrilling, and perhaps terrifying journey of discovery.